All right, hello everyone. I'm Dallas and I'm a master's student in robotics at UCSD. For the second project in my motion planning class, we had the opportunity to explore some search algorithms and how they can be used in different environments to find suitable path from a specified start to a specified goal. So in order to tackle this situation, one of the other methods that I used, I made a previous video on A-star, but when you're in an environment where you can't map a grid, we need to use sampling-based methods as opposed to deterministic methods, where we're allowed to follow strict rules. So in order to face this situation, I built a Python visualizer application using the PIL or Pillow library. And I got to follow along with the tutorial from VDEngineering and really learned a whole lot. So I highly recommend checking it out and trying for yourself if you really want to learn the most. Before we get into the design details, let me first demonstrate the application. So I'll open it up right now. All right, so what we're looking at here is the Python visualizer for RRT that we built. And the program allows users to draw environments using Microsoft Paint, actually, save them as PNG files, and then upload them to the script. So, for example, this is one of the more complex environments that I drew. I put that for my class to be funny, but I wanted to see if the algorithm could actually make it through these very complex tunnels and channels and things like that. But this was later stress testing. We'll look at some simpler cases first. Anyways, the visualizer uses these images as the configuration space for the RRT algorithm to find a path from a start point to a goal point. And the script converts these images into a grid map where white pixels represent free space and black pixels represent obstacles. Let's go ahead and take a look at some of the implementation details, most notably the tree node class here. So the tree node class represents each node in the RRT tree, stores the location of the node, its parent, and its children. Let's go ahead and look at the RRT algorithm class. So the RRT algorithm class implements the RRT algorithm for us. And some of the key data attributes include a random tree, which is the root node of the RRT tree. We have the goal, which is the goal node. We have the nearest node, which returns the node nearest to a sample point. We have the iterations, which is how many times you want to run the algorithm. We have a grid, which is the environment. We have a row, which is the step size that we want to take every time we branch out in RRT. We have the path distance, which is the total distance of the path found at the end of the algorithm. We have the nearest distance, which helps the algorithm find the nearest node to a node that it just sampled. We have the number of waypoints, which is how many waypoints are in the path. The thing about RRT is it doesn't always find an optimal path, but it will find a path for you, even if it's not the best one. And we have the waypoints, which is the list of waypoints in this path that it finds. Some other functions that are crucial for this implementation is adding the child. So this adds a new node to the nearest node in the tree and sets the parent of the new node. We have sampling a point function, which is randomly sampling a point within the grid limits within our environment. We have the steer to point function. So this is how RRT knows where to go or where to branch. And this function generates a new point by moving a fixed distance or a step size from the start node towards the end node. We have boundary checking. So this is an obstacle right here. And this is responsible for checking if the line segment from the start node to the end node intersects any obstacles or any node that it samples. Whether there's an obstacle in the path, we get rid of that node. We don't want that. It's not valid. Next, the more important ones are the find nearest, which is a function that finds the nearest node in the tree to a given point using Euclidean distance here. So that's the metric we're using. And in addition, we have the retrace RRT path function. And this one's important because this function retraces the path from the goal node back to the start node by following the parent pointers and storing the waypoints. So this executes at the end of our algorithm. So how does the whole thing work in operation? It goes like this. You load the grid and you set parameters. So that's what we're doing here. And here we specify start and we specify goal. You'll see that I have to adjust these for different maps, but typically you just pretty much, it's eyesight. You're gonna wanna look at the grid, figure out where your start is, where your goal is. So you load the grid and set the parameters and the number of iterations and also the step size. So I noticed in more complex environments, you're gonna want a smaller step size, especially in that one I showed you here. To get through these small intricate places, you're gonna want a small step size. And that's why I have 30 here and high iterations too, because it tends to explore a lot when it can't find a path quickly. So next you're gonna initialize the RRT algorithm object, which that's how we operate RRT. Then this is going to iterate through the specified number of iterations, sampling points, steering towards them, and checking for obstacles, and adding valid points to the tree as we go along. And then in the end, we trace back the path right here. So this is after the goal is found, you're going to trace back the path from the goal to the start and display the waypoints. So this was a really fun implementation, but talk is cheap. Let me show you some actual footage of this baby in action. So let's get to it.